equation. Let's write down the equation here. The form is written as this: y square, x square, y double pi plus x, y pi plus x square minus n square times 1. N is a constant, and it's not necessarily integer. So although it's used n, but it can be a real number. Sometimes if you generalize that, you can even use complex number. But most people consider real number. I mean, the Bessel equation in Bessel function that later on I think chapter 13 or 14, right? Later on we'll talk about Bessel function. We start with n equals integer, so the integer order of Bessel function, but it's quite straightforward to generalize that to real number, real n, or real order. Okay, and then the equation is not exactly in the general form we talk about when we talk about general form, where y double prime plus p y prime plus q, right? So to compare with that, you need to divide the x squared. The p for this equation is 1 over x, right? Divide the x squared here, so 1 over x. So x equals 0 is a regular singularity because it's just 1 over x is not more singular than 1 over x. It's exactly 1 over x, so it's regular for the p criteria. And for the q is 1 minus n squared divided by x squared. That's singular at 1 over x squared. It's still regular because for the q to be irregular, it has to be singular more than 1 over x squared. So it's still regular. X equals 0 is regular. And if you go on to analyze the infinity, you see that there is irregular singularity. So the table 7.1 also pointed that out. But we're not doing that. So between 0 and infinity, there's no singularity. So it should be a good choice to do expansion about 0, because now you would expect that the expansion should be valid from 0 to infinity, because within it there's no other singularity. But we'll see after we get the coefficient or the recurrence formula between the coefficient of the power series, then we can look at the convergency, right? And then see what the range of convergency of the series. Okay, so we'll do exactly the same as what we did. So just assume that the x is, or the y solution is of the given form, the standard form, j from 0 to infinity. Again, 0 is still a general situation because we add an arbitrary index s to the power, so that you have the freedom to set the initial term is a sub j. Okay, start from 0. Okay, and then determine what s is. So once we have that, we need other terms. So we need y here. And n is a constant, so a constant times y is just whatever constant times this. And then we also need the x squared times y. And then x times y pi, x squared times y double pi. Right, so now we can get the derivative first. Y pi is sum over j. And then j plus s a sub j x a plus s minus 1. Okay, that's straightforward. And y double pi is sum over j. Do it one more time. S minus 1 and a j a sub j x j plus s minus 2. Okay. So and we are actually what we need is x times this and x squared times this. So we might as well now change the equation. So x times this becomes trivial because all we need to do is just get rid of this minus 1. Okay. And likewise, x squared times y double prime is just get rid of this minus 2. And so far so good. All three terms has exactly the same form, so we don't need to do the what I did last time, the shift. We don't need to shift that. All three terms, this one, and this one, we don't need to shift. But then the last one, we need to do that because you have x squared times y. The x squared times y will be, this will be plus 2. X squared times y will be a sub j x j plus s plus 2. And now if you follow my method, I would want to shift this, the j, the index, so that this also have the same form x to the power of j plus s. And to do that, I'll call that j prime plus s, the j, using my method, plus 2 is j prime plus s, the j is j prime minus 2, or j prime is j plus 2. Okay, we just figured all this out and then substitute in here. J is j prime minus 2. And this is just what we start out to do, j prime plus s. Now you figure out the index, the summation limits. So j is 0, meaning j prime is start from 2. J prime is from 2 to infinity. And the infinity both are the same. So infinity. Okay. And the last step is to get rid of the prime. Once we did that, we get rid of. That's my way to do it. You don't have to exactly follow my way. So if you can see through it in one step, that's fine for you. Okay. So now we have all 4 terms in the same form, and then we can substitute all these into the equation. All right. So that's what we do. But you need to consider the sum of the summation, not all the same. This one start with 2, all the others start with 0. So you have 2 terms from 0 and 1, you only have three terms. Only start from 2, then you have all 4 terms. So you probably need to write out the 0 and 1 term separately. Okay, and what we can do is write the summation first and then write the 0 and 1 term separately. So sum over j from 2 to infinity, then you have all everything, right? And then everything proportional to x to the j plus s. Right, so you have 3 terms, and all these 3 proportional to a sub j, but this term a squared proportional to a to the j minus 2. So you have two kinds of terms. So all the a sub j terms are this one. So you have j plus s minus 1. That's from here. And then you have the x, y prime term. J plus s. Right. And then the n minus n squared term, minus n squared. right? That is n squared times this, and all these are proportional to a sub j. Okay, and finally you have this term square times y, which is nothing but just this minus n squared a j minus 2. Everything proportional to x to the j plus s. Is that okay? Yeah. Now the the 1 and 0 terms, so it will be exactly the same because all these three terms have 0 and 1 term. This one doesn't have. This one is what gives you the this is the, wait, did I miss a term here? 1, 2, 3. Oh, I don't have an n squared. This one shouldn't have n squared. This is from here, right? No. This is from y, right? No, x squared times this is this one, and I'm missing this one. So mine, this is y. This is n squared. This is n squared. N squared is y. N squared times y. This one n squared times y. Right. It's this one I mess up. This is x squared times y. This doesn't have the n squared. Right. That's this. Right. That's more like it. Right. So the only this one doesn't have j from 0 and 1. Right. So I have the other terms. J equals to 1 is 1 plus s. 1 plus s minus 1 is s. And plus 1 plus s minus n squared times a sub 1, and then 0 plus s, j is 0, so you have s times s minus 1, and then plus s minus n squared, right, a sub 0. Right, everything add up to be 0. That's the equation. Is that okay? So that's transforming the differential equation to this summation series. Okay, and now the initial relation or initial equation is the last one, because we require a sub 0 to be non-zero, then the coefficient need to be 0. And now they simplify that. So you have s, and then you have minus s here, so you cancel this with this one. With this one, the initial condition is just s squared minus n squared equals 0. S equals to n or minus n. Or simply, if you don't want to write like it, you just say s equals to n, but then keeping the choice, it could be times the sign, times the sign. Right, so it's, it can be positive or negative. If you choose n as a negative number, basically you choose this one. If you choose n equal to a positive number, you choose this one. But then obviously you assume n equals to n is positive. But in the original equation, n, whether n is positive or negative doesn't matter because it's n squared. So you have a freedom to choose n is positive or negative. You choose it to be positive, then you can s equal to n will be positive, minus n will be negative. But then you can say that you just choose s equals n, and then keeping the freedom that n can be positive or negative. So it doesn't matter. So the two kind of solution, two term, you can collect that to the one, and that simplifies the situation, so you don't have, because the recurrence relation will be the same, whatever you whatever sign is, you get the same recurrence formula, and you can just choose the sign of n in your final recurrence to get the maybe different series. Okay, and so that's what we can do. Now, once you choose the whatever your solution, you check the a sub 1 term. Now you choose, see what this is. This is S. There's no simplification. Did we have 1 plus 1? Yes. Yeah, this is right. So 1 plus S. This is like 1 plus S squared, actually. 1 plus S times 1 S plus 1. So 1 plus S squared minus N squared. N squared is S squared. So you have, but this one, this bracket is right here. This bracket is 1 plus S squared minus N squared. We substitute S squared. N squared is just S squared. S squared. The coefficient. So this is like cancel the square terms of 1 plus 2S. And that is unlikely to be zero, generally non-zero because S is N, unless N is minus 1/2, then it's non-zero. So you can just generally set it to be non-zero. There's only one special case that is zero, but anyway, for the general case, you can, because the coefficient is non-zero, then a sub 1 must be 0. You need to set a sub 1 to 0. Okay, so and so now the solution will be this one. So you start with the S is N. So that's the choice of whether N is positive or negative. Basically, is saying that if N is positive, J start from 0. You start from A to x to the N power, which is a positive power, which will be regular at the origin. So that's fine. And if you choose a negative sign, then the first term will be x to a minus power, a negative power. So that is singular at the origin. But that's fine. We'll discuss that a little bit more later. But so for S equals N, you can now solve the recurrence formula from this one. So this the curly bracket need to be 0. A sub j is equals to a to the j minus 2 divided by the square bracket. Now, but then that need to simplify because S is N now. So to simplify that, we can simplify that by cancel this one with the minus sign first, right? And that becomes just j plus n squared minus n squared, which is j plus n squared minus n squared. Again, like that one. The n squared term cancel, so you have j squared plus 2jn, right? So that's fine. And now the recurrence means because we set a sub 0 to be non-zero. So if you choose j equals to 2, then this will be a sub 0. The a2 will be a sub 0 divided by 2 times 4 times 1 plus n, or 1 plus n. So you can keep doing that, right? And then once you have j2 and you put j equals to 4, then this is j2, and then you get j4, and then you say 4, you get j6, and so on. So you get all the even j. And likewise, if we substitute a sub 1, if j is 3, then this 3 minus 1 is 3 minus 2 is 1, so a sub 1 is 0. So a3 is 0, and a5 is 0, and so on. So all the term with the index, odd index will be 0. All the even index, terms of even index are given by this recurrence formula. Is that okay? So that would be the solution. Now we can, I mean, this, you can say this is the end of it. that's give you algorithm to calculate that. But if you like, you want to try to see if there is a closed form for the coefficient a sub j as a function of j, and let's see, because that will allow you to write the series in a nice form, because that would be it's just a function of j. Right? And just like what we did last time, we can just try a few terms and see if we can recognize the pattern, right? Let's give some more space and see what we have. The a sub 0 obviously is just trivial. So a2 is a sub 0. And now what do we have? Divided by 2 square. And you can, multiply j out and get the j out. J is 2. And what you have is j plus n, or n plus j. It doesn't matter. J plus n would be 2 plus n, or the other way around, n plus. That's fine. So j 2 plus n. This 2 plus 1, 2 plus n. Right? Where j is 2. 2 times 2 is 4. So you have 2. 2 plus, 2n. Right? You can say that 2 is 2 or 2 square 1 plus n. Either way, we don't know yet, because we try to get the pattern. We don't see a pattern yet, right? Can you see the pattern? No, not yet. So a sub 4, let's give it some space. A sub 4 will be a sub 2. Like, again, you pull out j, which is 4. And then j plus 2n. J is 4 plus 2n. Right? And now which is now, you can pull out another 2, but we'll see what is more convenient to get a closed form formula. So a sub 0. Originally, you have 2. You have another 2. You can multiply another 2 out, and this is 4 is 2, or 2 to the 8, or 2 to the 2 to the 3 power 8, right? And then you have 2 plus n. Right, that is from here, but then you have another. This 2 to the 2. Yeah, this is from here, but then a sub 2 is this one. Another 2 to the 2 power 1 plus n. Right. You see a pattern? One pattern is you keep increasing this one. Keep increasing this one. You might as well write it like a sub 0, because that looks like that looks like factorial, but factorial only defined by integer, if n is integer. Now, if n is not integer, you can actually use something similar to a factorial function. Is the gamma function that we'll talk about. So basically, factorial function is n factorial is gamma function of n plus 1. So if n is integer, this is correct. But if you don't have, if n is not integer, you don't have factorial, but you still have, this is still defined, right? So whatever we say is factorial, actually you can recognize that or regard that as a gamma function with non-integer argument, right? So we'll still use factorial first, and then you see that this is like if you write like a sub 0 n factorial over here, and 2 square, and that will be n plus 1 factorial. That will be, yeah, that will cancel n factorial from here, then you get 1 of 1 plus n here. Okay, and likewise here, you use n factorial here, then you have, well, you have all this power of 2. We'll see how this all this power of 2 will get to a closed form. This n plus 2 factorial. Right, that's so we take care of all this n plus something power with this form, so that that looks at least up to this part is you have a pattern. Now, what we need to recognize, this is what is that? So every time we this is coming from the 2, right? Every time you have a 2 to the 2 power, with this one you get I think one of that is from the 2 to the powers. So you have 2 to the 2, and let's just we make also do one more factor. A sub j x a to the 6th power of a to the 4th. Again, you get the j out. J out is 6, right? 6, and then j plus n. J plus 2n is 6 plus 2n. You can write like 2 and 3 plus n. So one of the two factor of 2 is coming from this. You have 2n is here, pull out a 2, and then this is also all this even power. So you might as well write it like a4 is 2 times 2. This is 8 is 2 times 3, right? And then so this will be this 3, right? And then each time, each iteration, you pull out a factor of 2. So like for this one, you have a factor of 2 that's coming from this being even. This is 2 times 2, right? Then you pull out every time you also pull out a j, right? So it will be j is wait. J is 2 times here. So you have a 2 here and then a 2 here. And you have a j here. So that would be let's write like this. So you have 2, factor of 2, and then a 2 here. Now, sometimes it's you need some iteration. So right, n plus 2, and you have one of the 2 is coming from the taking out this 2. The other is from the 2j. If this is 2j. Oh. Right. And let's just write out first. 8/4 is this a sub 0, n factorial. Still keep the n factorial. And then this is n plus 3 factorial. How many factor of the 2 here? So you have a 6 times 2. And then this is 2 to the power of 6, right? And 6 times 2 is 3 times 2 also. So 3 times 2 times another 2, right? That seems like there's a factorial also from here. It's 3 times 2, right? This is 3 factorial. And then, say it again?
The last is to the power of 5 because it's 2 power 3 plus.
To the 5. Right. Okay. And now if we keep that as factorial, then 3 plus 3 times 2, and that would be 6 factorial, and 2 to the 6, right? 2 to the 6 power, 3 factorial. And we keep it like this is 2 factorial, so you keep a 2 here, and then put 2 here. This is 2 to the 4th. This is 3 times 2 times 3 to the 6. Now 4 is this exactly the same 4. 6 is this 6. But then you get a factorial out. This is 3 factorial. This is 2 factorial. And then this is 1 factorial is this 1. And then 2 to the 2, which is this 2, right? Now we can now generalize that to a sub. Now write like 2 times j. The different j's. We define your j. It's like j becomes 2j here, right? And now our pattern will be a sub 0. I get I get totally outside. Actually, a little bit outside of it. Yeah. Just make it okay. Okay. Let's write it here. Let's do some space here. So the general pattern is a to the 2j. There's a sub 0, n factorial, and then you have a 2j, right? This is j factorial. You have a j factorial, and 2 to the power 2j, which is this and that one. And then n plus j factorial.
Plus 1 there will always be
2j. Why is this 2j? This is 6. This is 6, right?
Yeah, but
this is I use it as a factorial. This is 3 times 2 times 1, right? Because compare with that, this is 2 to the 4 and then another 2. So this is 2 factorial, right? And then like this is 1 factorial and 2 to the 2, which is this 2. Okay, and so that seems to be the format. The easiest one to look up the textbook is did they get the same form? Oh, did I miss a negative sign? Why did I miss a negative sign? Did I get a sign wrong? Why did I get the sign wrong?
x square is plus, so it is plus aj minus.
Did I again?
The last term is plus there, that's plus aj. Because it's x square minus l. So x square is plus.
Yeah, this is plus, yeah. Okay, so it's only changed the sign. But it changed the sign in every term. So yeah, so a, so that would be at first it would be negative. This will be negative, right? this will be negative. But then when you change the a sub 0, it becomes positive. That is right. Negative. Change to this is be negative. So you have a negative 1, and h1 is depends on each iteration. You increase this j, the new j by 1. So it's -1 to the j power. Okay, -1 to j power, j factorial, and what else? 2 to the 2j, j factorial n plus j factorial n factorial. Yeah, that would be the right answer. All right. The last step is not essential, but sometimes it's taking some guesswork to do it. But that would be the final form in here. It's okay. So, but there's a little bit more discussion because now remember that our n has a sign. Right? We already said that we have a freedom to choose n is positive, negative, and now we need to think about what that means. And now we can, that's all those are intermediates that we can now erase most of the, not very good because I want to keep this one. I want to keep this one. So these are intermediates. We don't need those anymore. I need that. But once we have that, we can write down the solution. Y is sum over j from 0 to infinity. Now you have -1 to the j power, n factorial, or you like the way the gamma function that will include the general real n sub 0. And 2 to the 2j, j factorial, j. Okay, and then the x to the j plus n. Now keeping in mind that the n can be negative, right? So that's the solution, the form of the series solution. Now there's two cases. One is n is integer, the other is real. For a general real n, not integer, non-integer n, then obviously first you need to change all this factorial to the gamma function, but which is fine. And then then you will actually get two solutions because if it's real, then that real number can be positive or negative. If it is positive, then you start with a, but because j is start from 0, you start with x to the n power, positive power, and so on. So that is fine. It's regular at near the origin. So that is totally valid solution. But if n is a negative real number, you start with x to a certain negative power. So near x equals 0, it will be singular, but which is fine. Which actually, as long as you don't need to include 0, right? And so that is also a valid solution. So you actually get two series solutions for real non-integer n. So you either n is positive or negative. You get two series, and you can also show that they are linearly independent. And to check that, actually, we need to go to the next section. But then later on, you can check that by that method. We'll talk about it hopefully quickly, right? And so there are two solutions for real n. Now for the other case is n is integer. Now integer, you can keep all the factorial, but then there's a possibility that n is negative. Now we need to think about that. If n is positive, then everything is fine. So everything is regular. So all this n plus j factorials are all defined and so on. So that is fine. Now the troubling case is if n is negative, a negative integer, right? Because it means that you start with a negative integer power of x, which is not the two series of problem. It's just you have singularity near x equals 0, but the problem is the iteration. Now, if n is a negative integer, then they start from 0, and it's an integer keep from 0 to 1 and 2 also, right? So so somewhere along the line, so this the denominator is just j plus 2n, right? But if j equals to minus 2n, so this is 0 for j equals to minus 2n, right? And remember, n is negative integer, so it's this is positive. So start from 0. So eventually you will hit the integer 2n or minus 2n, right? So it's a positive value, so it's 2n. Actually, absolute value. It's a positive number, right? So somewhere along the line, you get into trouble for n is negative. Okay, so that means the denominator is 0, then the a sub j will be infinitely larger than a to the j minus 2, and the series is undefined. After that, it looks like it's undefined after that, or at least at that term is undetermined. So you get into trouble for the n is minus infinity, minus negative integer, right? And the way to actually do it, this is, the textbook didn't talk about that, but the one way to think about that is now your series, instead of starting from 0, it means from 0 up to when j is minus 2n, all this, because j to the minus 2n will be infinitely larger than the coefficient in front of it, right? If all the coefficient in front of it is regular until this becomes infinitely large. So you might as well set all this to 0 and start with a to the minus 2n power, so minus 2n. And start with that and then start the iteration at that point. Start the iteration at that point and then keep moving forward, right? And so that is the negative integer. So in that case, we can write that kind of solution, say y, in that case, we start with j from minus 2n, right? So j is from minus, which is a positive number, right? Or you can say, now we're saying that for this case, we're keeping n can be positive and negative, but if we, in this discussion, we just say that we choose n to be negative n, so change n to be negative and to the negative n, and so that the symbol n is positive, right? You explicitly consider the minus sign, take the minus sign out, right? So you change everything. This is just basically a label. Just you can change n to the minus n here, n to the minus n here, right? That doesn't change anything. The only thing changes that when we say that j start from minus 2n, actually if we treat n is positive, then j is start from 2n, right? For a positive one, and then to infinity. right? And then everything is fine. Right. You have this because now it's somewhat confusing. At least at first we say this is n. It has a sign, so minus. This becomes this is a negative number, right? This, so we can now, but because that is a little bit confusing because of this factorial. Everything it becomes a negative n factorial, and let's see. We can either go back to the original one and start with minus n, right? And start with s is equals to minus n and see what we get, because that is let's just keep this as n factorial, because because minus n minus negative factorial doesn't give you any. I mean, it's not well defined, but this n changed to minus n. And say that again, which one?
Is x to the power of 2j?
Oh, yeah, right. TJ, yeah. X to the TJ. Yeah. Yeah, right. Yeah, right. That's a general series I wrote it here. So, and right. Yeah, I got you. So this J and that J is not exactly the same. This J, this is still AJ, right? And yeah, supposedly that I need to. This actually start from. It's still this J is start from 2n, so it's actually start from n, because I multiply this by 2, so it's an n from that will give you 2. The old one is minus 2n. Right, this is just n. Okay, and j factorial and j minus n factorial. And j start from n, so that is fine. So j minus n factorial. Right, and I think I'm all time. Almost all time. Now, the last step will be like what we did, because we want to shift this, shift the j also, right? Because that start from n, we want to start it from 0. So we want the series start from 0. So basically now j, again, I'm not that. So j prime will be j minus n. We define a j prime, so that j prime will start from 0. It means j is j prime plus n. So that is fine. So it's minus 1 and j prime plus n, and then you have n factorial. Keep n factorial, and then the x j becomes j prime 2j prime plus 2n minus n becomes 2j prime plus n, 2j prime plus n, and then divided by, there's a sum over j now. j pi is from 0 to infinity. Okay. And 2 to the 2 j prime plus n. Right. And then we have this j prime plus n factorial. And this becomes j prime. This j minus j prime factorial. And what do we have here is we're just trying to compare this. So this one, there's an a sub c. I mean, there's an arbitrary constant, which we might as well call it a sub 0 also. But just formally call it a sub 0. Compare this with that, because now this is there's a sub 0 here. There's a constant with 2 to the n, which is actually we can absorb this 2, because this is 2 to the 2j, this is 2 to the 2j plus n. So there are 2n, but then this 2n is just a constant. It doesn't affect the solution. It's not the function of it's not a function of x or j. So that you can absorb that as a constant. 2 to the 2j, 2 to the 2j, and then j factorial, j plus n factorial, x to the 2j plus n, x to the 2j plus n, minus j. The only thing changes is this minus 1 to the n. Otherwise, the same as that one. So you can, if you choose this a sub 0 as the same as this a sub 0, this becomes minus 1 to the n power y. No, if we call it y sub 1 or y sub n, this is y sub minus n. This is y n. Right. So all this is to show that in this case for integer, if n is integer, then the second solution actually is linearly dependent of the first solution. So the two solutions are not linearly independent because exactly they are proportional to each other. There's a proportionality minus 1 to the n, which is still a constant. So this fail. The second series does not give you the new solution. So, right? And that so this is a general situation. Later on, when we talk about Bessel function, the negative integer Bessel function has this relationship minus 1 to the n that we define explicitly like that, so that they are defined exactly like that. So it's coming from the fact that the series solution, you can only get one linearly independent solution. The second one, if you use a series, you get a series that is linearly dependent on the first one, just proportional to that. Okay, so that is that we'll find out the second solution later on after we finish talking about the general formula to get a second solution. But let's finish. Last time I think we almost done with the Bessel function series solution. I mean Bessel equation for the. We derived the general form. That there's just a little more discussion based on the form. So last time we kind of get the solution y, and this it depends on this parameter n, which later on we can identify. It depends on n, or we can actually just use the usual label, the Bessel function j sub n. Last time we finally got it after some struggle. J factorial n plus j factorial over 2 n plus 2j. Okay, so this is a form, but let's look at the properties. And this n parameter is in the Bessel equation. It doesn't have to be integer. If it's non-integer, obviously you need to change those factorial to gamma function. So because factorial defined only for integer. So that's one thing. And for non-integer, for any real number n not integer, this actually valid for positive n or negative n. So the n, for positive n, obviously that defined, and the series is nice and also finite at x equals 0, the point you make the expansion, because it's x to the power n is positive power. For negative n, it's still defined because gamma function for real argument is defined unless for this negative integer. And but then for even for real number, a negative number will make this singular near the origin, which is fine. So you get two linearly independent solutions. One is regular near the origin, the other is singular, which is fine. It's a property that for many of these second order ODE near a singular point. This is a regular singular point at 0. So it has one regular solution, but the other is singular. But the solution otherwise is valid. So it's still useful, that function, that solution, because sometimes we don't use the full range of the domain of the function. Sometimes when we have a given problem, if our boundary is not at exactly at 0, it starts from somewhere finite, then that solution is actually need to be used actually. Okay, so that's for non-integer n. For integer n, obviously that defined for positive number. For negative number, that we showed last time that the recurrence formula somewhere along the line, the denominator becomes 0, and then it broke up for the next coefficient. And in this form, you can also see that if n is a negative integer, and j is positive or 0 and positive, and somewhere that this j before actually says before a certain number, this is a negative number. So if n is negative, then j from 0 to n, that is all a negative integer, and this gamma function at the negative integer, then they actually are singular. So in another way to look at that, because it's singular, then the coefficient is 0. Then the last time we actually showed that if you sum this series from, I think for this, well, it's summing for n. I think it's last time we struggled a little bit. Then we actually showed that we have for Bessel functions, j minus n is minus 1n jn. So they are linearly dependent. So for integer n, you only have one. The series solution only give you one solution, or one linearly independent solution. So you need to find a second solution, which we'll talk a little bit about that. Not too much, because it's getting complicated, but we'll list the general method to do that. Finally, you can look at convergence, because once you have a series solution, you want to know whether it's converged or whether it depends on x, because this is a series that's a function of x. So for what x that series is convergent, or is there a finite range for x? And for this one, we can go back to the recurrence formula, or just look at this coefficient and then take the ratio. You can say like if this is like whatever that is the term, what is it? So this is c sub j, right? And take the ratio test, and c sub j plus 2 over c sub j, right? C sub j itself is, you have j factorial n plus j factorial, right? And then it's in the denominator, so get it back to the numerator, and then the x over 2, this ratio will give you x over 2, because it's jump over 2, that would be square, right? And I should say plus 1, because this is defined as each integer, and the factor of 2 is defined in this power of x, j over j plus 1. Right, so that is j plus 1 factorial n plus j plus 1 factorial, and cancel the factorial, that becomes j plus 1 and n plus j plus 1, right? X over 2 square. Okay, and for this series, it looks like it's always converging to whatever value of x. But x can be large. You can let x becomes tends to infinity. But when you take the ratio test, you want limit of j goes to infinity, right? And limit of j goes to infinity. That will goes to, because you have 2j in the denominator, so whatever x value, that will goes to 0, right? And so it's always converge for any x, or x goes to infinity, or the range of convergence is actually infinite for x, right? So that is a nice property for Bessel functions. It's all, at least the series solution is always convergent. And the reason, you can go back to the table in the last section, that the Bessel function, the next singularity is at infinity. There's an irregular singularity at infinity, and there's a regular singularity at x equals 0. So there are only 2 singularities for Bessel equation. So when you expand on the regular singularity at x equals 0, the limit will be from that to the next singularity, which is infinity. So you have a convergence. The radius of convergence is actually infinite, which is nice. Okay, I think that's all for the Bessel function series. Okay, is it? All this. So that would be the conclusion of this discussion. And the last part of your section, yeah.
Last week we had an factorial.
Yeah, it's because that doesn't depend on this. You're talking about this n factorial, right? This one doesn't depend on x or j. You can take that out. You can always take that out and redefine your function, because this is a linear equation. Any constant, you can multiply by any constant, is still a solution. And the Bessel function is defined without this n factorial. So it doesn't matter n factorial. N is a parameter. It's just a constant, or whether it's real, n is real or integer, it doesn't matter. Also, the factorial or even gamma function of n is still that's a number. Okay, you can do that. And yeah, I think that is part of the struggle that last time we tried to divide this. It's just basically there's one more argument that if we normalize everything, this series, then we can show that you have this one. So like if you use this one, then to show that this is easier to do that. Okay, and all right, so that I guess that's it. The last part of the section has some discussion on some general property when you do expansion in regular or irregular singularity. And well, I will let you read the discussion because we don't have to go to too much details. Just the general idea is if you expand in based on the irregular singularity, you likely won't get any solution. For regular singularity, you can get a series solution, but sometimes you can only get one solution. If like most likely, if you have the initial condition, you have two solutions, and if two solutions it's different by an integer, then sometimes the other solution is linearly dependent on the first one. Then just like here, you don't get the two solutions, right? So that's the general idea, but in the usual case, you just do it, do the expansion, and then see what happens.